Alright, good afternoon everyone. We're going to go ahead and get started with the atomic structure. Now, some of the basics you may have remembered from earlier sciences, and for those things we want to make sure you keep those things fresh. But for the things that are brand new, you want to make sure you take note and write down again any questions that you may have. Now, let's get started. Our learning goal for this part of this video is going to be that you'll be able to distinguish between the different subatomic particles and be able to demonstrate and represent electrons according to the models that we're going to use, which are going to be the Lewis structure or Lewis dot structure and the Bohr model. Let's get started with our subatomic particles. Now, in terms of location, charge, and mass, we want to make sure that we can differentiate between our three subatomic particles. First being our proton. We usually think proton positive. When you're pro something, you'll usually be positive about it. It's going to have a mass of 1 atomic mass unit. And of course, this is a relative mass. I want this to be known. Is a relative mass. What does that mean? It's slightly above this, but we round it, of course. Now, relative charge, +1. Make sure you're noting that it is +1, not just 1, and not just positive. And it's going to be located inside the nucleus. Now, neutron also has about the same relative mass, but this time we have no charge being involved. We have a charge of 0, or most times how you actually see it is there'll be a nice little line right through it. This is also going to be located inside the nucleus, as you can see with the model given up to the top of the page. Now, the electron is the one that's slightly different. If you look at the relative mass, you notice that it's going to be much, much smaller. 1 divided by 1,840 AMUs. Now, because of this, the mass of the electron really doesn't factor into the mass of the overall atom. But the overall charge will still be very important. It's going to have a charge of -1. Now, the last part here, you notice it says outside the nucleus. I've had some tell me, and even mark on tests, that the electron is outside of the atom. No, it's still a part of the atom, it's just outside of the nucleus in the electron cloud. Now, looking at this basic information, we're going to focus in on a couple of different things. We're going to focus in on what happens when we change the neutrons in the next unit completely. But what happens when we change the number of electrons, or how do we actually represent those electrons? Now, what defines an element? That's going to be our atomic number. So if you look at the periodic table, and you look at the numbers that are all throughout the box, the one that's usually given to you is a whole number, and they increase as you go from left to right and as you go from top to bottom. This is going to tell you the number of protons in the element. It's going to be the same for every atom of that element. If I change the number of protons, I change the element. So you want to make sure you keep that in mind. Now, how do we find the number of neutrons? So one little note that I forgot to put on the last slide, if I know the number of protons because it has a positive charge, the other thing that I also know is I know the number of electrons. Well, how do I know the number of electrons? Each of our atoms is going to be neutral in charge. So that means if I have 3 protons, like lithium, that means in order to keep it neutral, I have to also have 3 electrons. This way the charges balance out. Now, with this being the case, that's going to take us now to where we just were with our neutrons. How do we find the number of neutrons in the atom? The first thing that you're going to do is, I'm going to give you a little formula that can help you to write it down, or help you to remember. Mass number equals the number of protons plus neutrons. Now, with that being the case, if I'm trying to find the number of neutrons, all I have to do is rearrange this in order to find it. So I'm going to take the mass number minus the number of protons will equal my number of neutrons. Now, this mass number is basically just going to be, if I take the, sorry, let me write it over here. If I take the atomic mass and round it. You notice that's what's set up here at the top. I'm going to take the atomic mass, round it to the nearest whole number. That's going to give me my mass number. Now, Once I have that, subtract the number of protons, the atomic number, from that mass, and that'll give me the number of neutrons. So this is something we're going to pay attention to, especially when we talk about isotopes. This is going to be actually very, very important, because isotopes, again, will be atoms of the same element that are going to differ by the number of neutrons. But we'll come to that in the next unit. Now, how do we actually represent the electrons in the atom? Two main ways we're going to use are Bohr diagrams and electron dot diagrams. Starting with Bohr diagrams. Easy way to remember them, we're going to call them the Bohr ring diagrams. Now, with that idea, we're going to go ahead and start looking at potassium. We're going to skip the card sorting activity. We can still do that in class if there are those who are still struggling with the idea. Now, keys for making your Bohr diagrams. First, you're going to draw a ring for each electron shell the atom has. Now, you'll know this by looking at the period or the row number that the element is in. Since potassium is in period 4, that means it's going to have 4 electron shells. So 1, 2, 3, 4. 4 different levels that are there. Now, for the Bohr diagrams, I have to add the dots for how many electrons are there. So, looking at the periodic table, I find that potassium has 19 electrons total. So, I have to fill them in, but I have to fill them in, one starting from the center and working my way out, and I have to follow this pattern. The first shell only holds 2. The second shell can hold up to 8. Third shell can hold up to another 8. Fourth, 18. Fifth, 18. 6 and 7, 32 apiece. Now, does that mean that they have to have electrons on those levels yet? No, it's just saying that they have the ability if they have those available. So, if I'm looking here, I have my 4 rings, adding my 2 in the middle, my 8 on the second row, got another 8, and that leaves me with 1 for the outer ring. This would be my Bohr diagram for potassium. Now, what about electron dot diagrams? This is going to be the second set that we're going to use. Now, to make an electron dot diagram, we have to know 2 pieces of information. One, the atomic symbol, which we can get from periodic table. That one's great. And second, the number of valence electrons. Now, this word valence electrons is actually going to be a little important. Basically, the valence electrons are going to be on the outermost ring. So, when we looked at our previous example, if I can go back here, we noticed that we only had one electron, only electron on the outermost ring. That would be considered the valence electron. Now, if we're going to stick with potassium, we can work this out. Most people tend to love these. Potassium, the symbol is going to be K, makes life easy, and it has 1 valence electron because it's part of group 1, as we would have saw from our periodic properties video. So write the symbol, draw the dots around to show the valence electrons. Starting on the side, put 1 dot and then pair them up after we have filled in the 4 sides. So potassium, got K, and 1 dot. Just finished, everything's good. Now, if we were to look at one more example for this, let's look at sulfur. Sulfur, symbol is going to be S, capital S, and it has how many valence electrons? According to the periodic table, we have 6. So, I'm going to put 6 dots. And we're done. Now, this is going to bring us to the end of this video. If you have any questions, please let me know. We're going to do a little bit of practice in class. Make sure you guys have this sort of tied down. Have a great evening, and I look forward to seeing you in class.